then I'm going to switch over to talk about some tools based on generating functions and the notion of persistence. So I'll talk about persistence modules. GF-based capacities and homology, and how this sets up a persistence module in which we can get the result that we want, and then similarly go through the proof. So that's a rough plan. Okay, so first of all, the setting is the same as what Chu described. However, take rotation asymmetric Lugo form. So we're in ℝ2n cross S1. And contact structure is going to be the kernel of dt minus alpha L. Is the Lugo form 1/2 PDQ minus QDP. So I'm using a T instead of a Z, keeping P and Q for the coordinates in the base. And in order to contrast the different results that I'll be talking about and what Chu talked about, I'm going to just emphasize two different groups of contactomorphisms. So cont of ℝ2n cross S1, this will be compactly supported contactomorphisms. And cont sub 0. So I'll just actually drop this ℝ2n cross S1 in general, but cont and cont 0, the difference is that here we're looking at the identity component. Previous group. So that consists of time 1 maps of contact isotopies that are compactly supported. Okay, also there's a slight difference in our definition of the balls. So in ℝ2n, B of R is going to be set such that pi z squared is less than R. So I'm already absorbing this pi into the definition here. And then the pre-quantized ball radius R will just be the previous one across S1. Okay, so the next thing, sort of terminology related, is the notion of squeezing. So this is a notion that appeared in this paper of Eliashberg, Kim Poltrovich that you mentioned. And they define contact squeezing of some domain U1 into U2 to be an element of cont 0. That takes the closure of U1 into U2. However, in the paper, they prove non-squeezing and squeezing results in the strongest sense. So what I mean by that is you could imagine defining a squeezing simply as an element psi in cont instead of cont 0. So that would be a more general kind of squeezing. And I'll just, it's not terminology from EKP, but I'll just call that a coarse squeezing if we just require psi in cont. So the existence of one of these is a weaker condition than that. On the other hand, non-existence of one of these is a stronger statement than non-existence of one of these. So they prove non-squeezing by saying there's no psi in cont, and they prove squeezing by saying there exists psi in cont 0. Okay, so to go through the compare these results, run through them. So these are statements that you already mentioned. There's, first of all, a squeezing result. So they observed if R is less than 1, then squeezing is possible. Here we're going to be looking at squeezing BR into itself. This is another subtle, well, it's kind of trivial distinction. Here, notice that we're requiring the closure of U1 to go into U2, so it's you can ask this question about a domain into itself, whether you can squeeze the closure of the domain into its interior. It's not immediately obvious. They show that you can do that when you're dealing with a pre-quantized ball at the R with R less than 1. On the other hand, if you have an integer value of R, there's no coarse squeezing. Okay, so this is then the question here. This is only, sorry, this is R. So this deals with all the integer R. Then the question remains, what about other R that are greater than 1? And so we have choose result. If R is greater than 1, there is no squeezing of hat BR into itself. In fact, it's quite possible that this statement is equivalent in ℝ2n cross S1 to the existence of, to the non-existence of coarse squeezing. But just to state the difference here, I'm proving an analog of EKP's result, saying there's no coarse squeezing. And they may actually be the same. Okay, formally the second one is stronger, but it's probably not actually. Okay. So I should just make a comment about this theorem B of EKP. So what they actually do is they prove that hat B1 can't be squeezed into itself. I should say coarsely. And then they use a covering space argument to derive the statement for all integer R. And I'm going to spend a couple of minutes to go into that, because it's in fact this covering space, the covering map here, which is related to a natural ZK action, if you take a particular integer k, and that's the same ZK action that is being taken advantage of in this construction of ZK equivariant contact homologies. So in a sense, it's just it's using a similar strategy to what was in EKP already, but defining a ZK equivariant form of contact homology. Okay, so the covering space in question is the k-fold cover of ℝ2n cross S1 as a contact manifold. So this is the following map Once again, z is the coordinate in R2n and not the z from the vertical direction, which is now called t. Sending zt to square root k z kt. We just have to proportionally shrink in the horizontal and vertical directions. So this is a contractomorphism. And the deck-10 transformation group is zk. And so if you have a contractomorphism in either in cont or cont 0 of the base, this lifts uniquely to psi bar in cont, so this is of the base, and this is of the cover. And in particular, this will be zk equivariant. So let me just try to draw this. I'm going to look at what happens to domains in the cover and the base under this map tau. So because we're multiplying by square root k and by k, in a sense we're, let's say we have k pieces here. We're mapping each one to a wider domain. And if we take hat b r over k to hat b r. Okay, so the reason I'm mentioning this is because this means that we can relate non-squeezing down here with non-existence of zk equivariant squeezing up above. So in particular, a coarse or non-coarse zk equivariant squeezing of ek into itself corresponds to a zk equivariant squeezing, a squeezing, respectively possibly coarse, B1 into itself. Oh, sorry, I'm just saying this the wrong way. So here, here we are in the cover. Here we're in the base. So this broader pre-quantized ball in the base, not being able to squeeze that into itself corresponds to not being able to zk equivariantly squeeze this narrower one in the cover. Okay, so in EKP, all they use contact homology for is to rule out squeezing hat B1 into itself. And then they say if we could squeeze hat BK into itself for some integer k, then we could zk equivariantly squeeze hat B1, but we know we can't even squeeze it at all, let alone zk equivariantly. So a kind of observation here is that they're using a strong, they need only to rule out ZK equivariant squeezing of hat V1 into itself. That's actually all they would need in order to make their argument go through. But using contact homology, they've in fact ruled out any kind of squeezing of hat V1 into itself. Okay, unfortunately, this hat V1 is the only pre-quantized ball that contact homology can, or at least as they have defined it, that contact homology can be used to as a tool to prohibit squeezing. So it can only be done for hat V1. However, and so this is the main idea or the main motivation in defining a ZK equivariant version of contact homology. We can ZK equivariantly so in fact we can rule out ZK equivariant squeezing of hat V1 over L into itself for any L less than K. And this will then give rise to this statement here, which is another way of putting this, is that hat Bk over L, when L is less than K, cannot be coarsely squeezed into itself. Okay, so that means that the main thing that I'm going to just quickly sketch for you is ruling out of ZK equivariant squeezing of hat V1 over L. Okay, so let me just very quickly talk about this modification of the context homology that BKP used. So while the context homology they define is just mention this over here. Their context homology is a G functor, where G is equal to plus ℝ2n cross S1. Confounded domains to Z-graded vector spaces. And this will be a GK functor, let's say, where GK is cont ZK. So I did not define this group yet, but this is just those entactomorphisms in cont ℝ2n cross S1. Put it this way. Which happens to be ZK equivariant for the ZK action that I defined. Okay, so to just quickly mention this, and then I'll show you how we use it, and we'll move on to generating functions. The only difference is that now we consider ZK invariant contact forms. And as before, we're going to consider we look at forms that are on a particular domain that are standard outside, and all of that part is going to be exactly the same as in EKP. But we're just in addition requiring that these be ZK invariant for that tau, at the action generated by tau, which is a vertical shift by 1 over k. And we use ZK invariant almost complex structures. And as before, we define a chain complex where the generators are closed non-degenerate wave orbits. And the differential is defined counting full orbit cylinders. But here we're going to use ZK coefficients. So we're only counting mod k. Okay, so the upshot of bringing in this extra symmetry with the ZK action is that we get a chain complex with a ZK action. And we'll define CHZK. So ultimately, we're going to consider contact forms, as I said, which are standard outside of the domain, and we're going to be taking a double limit and so on. But individually, for a particular contact form, the group, the vector space in question, is going to be the equivariant cohomology of this chain complex. Okay, and then we take limit over forms, say these are permissible, forms, standard outside a domain U in order to get an invariant of the domain U. Okay, so the key property of this invariant, as mentioned there, is that it's a G functor, or actually GK functor. And concretely what I mean is we have U1 contained in U2. We have this contact homology of U1, and morphism from that into contact homology of U2. If we have a ZK equivariant contactomorphism, then we get an induced map. So this is a star, you could say, for the inclusion. This one will be a map from the contact homology of U to contact homology of psi in U. And these things commute. Let me just say that they commute, so we have to draw them. Maybe I should just quickly draw this so you can see what I mean. Do that here. So we have U1 mapping to the vector space for U2. And likewise, psi of U1 into the vector space for psi of u2. So here it's via inclusion, and then psi star, and that diagram, please. Okay, so let me quickly summarize the data that we have from already from EKPs using the version of contact homology in EKP, and then I can quickly show you why this contact homology gives us extra information. So the statement that EKP have is that this vector space of hat BR is going to be equal to ZK. Here I'm just converting. They have a statement in terms of Z2 with Z2 coefficients, but you can actually derive it for any K. The reason why they stuck with Z2 is to avoid orientation questions, but you can take care of that and get the same statement for any ZK coefficients. So we have this if P is equal to minus n minus 2n integer part of 1 over r and 0 otherwise. Whereas the statement with ZK equivariant contact homology is that we get a non-trivial group if P is greater than or equal to minus n minus 2n times integer part of 1 over r and 0 otherwise. So just to draw this and get a sense of how this works, I'm going to show you the degree P and just kind of graphically represent where these groups are non-trivial. So let's say we fix R2 less than 1 over L less than R1. And we're imagining trying to squeeze, by the way, I made a statement earlier about not squeezing hat B 1 over L into itself. That's equivalent to not squeezing a slightly larger ball into a slightly smaller ball. This is an open condition, squeezing a domain into itself. Okay, so let's just here imagine that we have R2 and R1 that are on either side of a reciprocal integer. I'm going to look at the degree P in the two cases. Let me also let M1, or I'll let HMI be 1 over Ri for those two radii. And so the degree is going that direction. It's kind of opposite from what you would expect. Makes it just easier to think of. So let's look at degree minus n, and then because R1 is larger, 1 over R1, in other words, this M1 is going to be smaller, so we don't go down as far. So let's say we stop here at minus n minus 2n M1, and maybe over here is minus n minus 2n M2. So we have non-trivial groups in all of these degrees here. And then continuing in this direction as well. And then below that stage, it's 0. Okay, so there's an additional statement here. You can show that given psi in cont zk, and psi of hat BR contained in hat BR. So psi is a squeezing of hat BR into itself. If you're in this situation, then this inclusion map, iota star, is an isomorphism in all possible degrees. So what I mean by possible degrees, so let me actually say this instead of it this way. I'll say we're squeezing R1 into R2. So what I mean by that is, here we have isomorphism etc. And then after this stage where the groups are just 0, of course we don't have any more isomorphisms. And the way this is proved, it's fairly easy to establish that you have isomorphism in degree n, and then you can use the ZK action to make an inductive argument that allows you to keep on unraveling that to bring this isomorphism down to the first place where the groups become 0. So you're kind of unwinding the isomorphism here down as far as you can go into these lower degrees. Okay, so what that's going to mean then, this is by a similar kind of argument to the one that you had sketched over here. We're going to use this to rule out squeezing past at B 1 over L into itself. So this is proof of, it's not now, but I guess it's proof of E. If you have R2 less than 1 over L less than R1, and some psi, which is ZK equivariant, such that psi of hat B R1 closure is inside hat BR2. Then we have let's draw these groups here. Hat BR1 is contained in. So because sorry, I want to do R2. We're doing a slightly different argument, but it's the same basic idea. If we've squeezed R1 inside R2, then psi has squeezed hat BR2 into something even smaller. So we have this kind of nesting here. Psi of hat BR2 is contained inside of hat BR1, and that's contained in hat BR2. And using this theorem, we have to have an isomorphism, so the corresponding iota star will be an isomorphism in all degrees. Using this theorem. And then we'll get a contradiction in the particular degree right here, in any of these degrees in between that one and that one. So in particular, right here, sitting in between there is going to be minus n minus 2n L. Somewhere between those. Okay, so that's in a nutshell the argument with contact homology. It's very similar to the original argument of Eliashberg, Kim, Polterovich. It's just that they really only needed to rule out ZK equivariant squeezing of hat B1. In fact, they ruled out any squeezing of hat B1 into itself, and they couldn't extend that. But if you are really only trying to get a statement about non-existence of ZK equivariant squeezings, then you can rule those out for these smaller domains, hat B1 over L. And that's what gives rise to this non-squeezing phenomenon. Okay, so now I'll switch over and in the second half talk about generating function argument using persistence modules. So the second proof, or the second, this argument that I'm about to describe proves the statement that that Chu gave. It doesn't rule out a coarse squeezing, like the argument I just gave. It rules out isotopic to the identity among compactly squared contact isotopies. So let me just tell everybody what persistence module is. So it's kind of fancy terminology, well not fancy, but coming from computer science, but actually it's just a functor from a closed set, usually R, to vector spaces. And so the point here is that if S is less than or equal to T, we're supposed to induce some map VST from vector space for S to vector space for T. Okay. And mostly when people started talking about persistence modules in computer science, they were thinking of R as a closed set. And they're particularly nice facts. You can encode a persistence module using interval modules. This is what's known as barcode. So barcode is just a graphical way of presenting that kind of decomposition. So there's this decomposition or structural theorems that give you that. And statements. Okay, but we won't go into that. We don't need that kind of thing right here. And in fact, in what I'm going to be talking about, we're not going to be using just R as the closed set. We'll use something slightly different. But in fact, the usual, so it seems like the introduction of this into symplectic geometry is relatively recent, but in fact it was, without that name, it was already, it's the basis for V-Toble's capacity and so on. So this is a concept that exists already, is used already in symplectic geometry. What's perhaps slightly different is that you can, in fact, use any closed set. So you can generalize that type of tool in that way. And also, of course, using these unique decomposition statements, you can get more out of spectral invariance and so on. Okay, so I guess I maybe will just say so I won't go into any of that about interval modules. Let me just quickly say an interval module is a persistence module where the vector spaces in question will be the field. Let's say the field is well, we can use some K. It's the field of coefficients for the vector spaces. And if you define vector spaces to be K when S is in a particular interval and 0 otherwise, then typically this is represented just by drawing the interval. And the maps VST, which are called persistence maps, will be the identity in here, and where the vector spaces are 0 will of course be 0. So that is what an interval module is, and you can decompose persistence modules in many cases uniquely into direct sums of interval modules. And that in fact corresponds to the Baranikov complex etc. Okay. So let me just tell you what the persistence of an element is. So let's let mu be in the vector space at level S. Then the persistence of mu is going to be the sup of T and R such that this transition map VST of mu is not zero. So taking a non-zero element in VS. So for example, if we took mu to be some generator here, then let's say that this interval goes from 0 to 1. And we took an element mu here, then its persistence would be 1. That's where it survives until they're under these transition maps. I should just point out this is a slightly different definition from what's used in computer science. In computer science, it would be the difference between S and T. So it's basically the lifespan of that element. But here it's simpler to make the correspondence with the beta bubble capacity and so on to just define it this way. The difference between them is just S, the place where the original class lived. Okay, so now let's talk a little bit about GF capacities, homology groups, and I'll describe some new morphisms to add to this existing framework. And with the help of that, we can set up a persistence module where the underlying poset is not just R, but something slightly different. And that will allow us to derive a non-squeezing result in ℝ2n cross S1. So first of all, a comment that beta Bose capacity, which I already mentioned this, and Sandon's capacities, for example, these are actually persistences of certain classes mu in a persistence module that I will describe here. So in a persistence module, essentially consisting of GF homology groups. And then I'll explain to you what I mean by that. So this is historically not the way it went, because you can define the capacities directly in terms of the generating functions without setting up these homology groups. So you don't need to set up the more persistence module and then take the persistence. But the sort of later work of Trainer to define GF homology groups, and then Sandon also defining that in the context setting. Once you have those collections of GF homology groups, they form a persistence module, and these original capacities are just persistences of certain elements in those persistence modules. Okay, where mu is it's related, I won't go into the details here once again, but it's related to the fundamental class of the base. So after compactification, so it would be ℝ2n or ℝ2n cross S1 in the symplectic or contact settings. Okay, so let me just leave it at that and try to quickly say a bit about these GF homology groups so I can tell you about the new morphisms. How many people are familiar already with generating functions? Shall I just give the definition of a generating function and then fine. Okay, so let's say we're given an exact Lagrangian L, or Legendre, so this is in T star S2n. Let's say I'll just actually say T star M, or Legendrian L contained in J1 of M, some closed M. And you should be thinking of them as being either S2n or S2n cross S1. And since we're dealing with compactly supported compactomorphisms, we first go through a compactification procedure before we get to this stage. But the definition of a generating function is that it's just some function S defined on M cross RK to R. And we'll call it a generating function for L if 0 is a regular value of partial of S with respect to the partial of C. Here I'm going to take C as the coordinate in RK and X as the coordinate in M. And L is just given as the set of X, the X at the point XC, where XC is one of these places where partial S in the C direction is 0. And in the Lagrangian version, it would be X partial S with respect to X, and then the value of S. Okay, so this is somehow, it's a generalization of the situation where L is the differential of a function, or L is the one-jet of a function. We won't be able to, if this original L doesn't project diffeomorphically onto the base, we're not going to be able to express it this way as a differential or one-jet. We throw in these auxiliary variables C, and then we achieve a similar thing. Okay, so that's the notion of a generating function. And a key thing here is the critical points of the generating function are in one-to-one correspondence with intersections of L with the 0 section or the 0 wall. So that's the 0 section cross R sitting inside this J1 of M. And then we have, I haven't talked about when the generating function is quadratic at infinity, but we want to impose that, and there are existence and uniqueness results for quadratic at infinity generating functions. So this is work Lamba Sikharov in the symplectic setting, Chikhanov in the compact setting.
Uniqueness is Viterbo,
Also, I think Viterbo claimed it, and then I think a PhD student actually.
Exactly, that's true. So the uniqueness actually, this is referring to existence, and here I should put 10A, or Viterbo 10A. And for our purposes, all we care about is that so it would take a while to define this notion of uniqueness, but the point is that it results in the homology groups of sublevel sets being well defined, being uniquely defined. And those are the things that we're going to take. Those will be the GF homology groups, and those are the vector spaces forming the persistence module of interest to us. So those at least will be unique, we determined.
And that you find these things with quadratic infinity, presumably that is why you can't do it, why you can only do it for isotopy.
So there's several reasons for that. The main reason though is that if you want to have you want invariance under contact isotopies, then one way.
The question back there.
Oh, so the question is.
Yeah. So because this method here doesn't only applies to contact isotopies.
This method of creating the generating function.
Oh.
So it works for, yes, I should say that this existence result is for L isotopic to the zero section. And isotopic by a Hamiltonian or contact isotopy.
Yeah, I wonder. So generally, I think people haven't really studied if one takes something which is not isotopic.
So there's this guy. I forgot now. He's on the spot. I forgot his name. Yes, so that has been considered. But I was just going to say that another issue for us is that we want invariance of the resulting vector spaces under contact isotopy. And so for that, even if we had created by some kind of magic, even if we had just created these generating functions, in order to relate the generating function for some L with the generating function for psi of L, the only obvious way of doing that is to follow the sublevel sets as you go along and make sure that you don't cross an integer value in the contact setting, or you observe that it doesn't change during the whole isotopy in the symplectic setting. So, I mean, that's, even if you were God-given these things somehow, you would still have that problem. Okay, and I have 5 minutes. Maybe I should just jump ahead quickly. So I'll just comment that was for, all this is in terms of a Lagrangian or a Legendrian. Given psi, which is either compactly supported Hamiltonian diffeomorphism or compactly supported contactomorphism, you can let's say ℝ2n S1 or ℝ2n, you can cook up a particular Lagrangian, exact Lagrangian or Legendrian. And this step, even though it's quite trivial, is actually the stumbling block where you cannot apply it, extend these methods to other manifolds. To produce this kind of graph in T star of M or J1 of M, it's not obvious how to do that in general. Okay, so we produce this L phi, and then we produce S phi that's associated to L phi, and then we note that phi 1 less than or equal to phi 2 with a suitable partial order. You can, in that situation, produce generating functions S for phi 1 and S for phi 2 that will have the same order relationship. And you define generating function homology group for a domain as a direct limit. So I guess I won't go into all of this, but here this means that these homology groups, which are equal, so here, these groups which are equal to the homology of let me call this E. And then here we're looking at homology of E relative to S less than or equal to A. Those will be the GF homology groups, and then the claim is that they form a directed system over a collection, a family of phi supported in the domain U, and we take inverse, inverse systems is what I want to say. That's because if you have a larger generating function, then you're going to get a smaller sublevel set. So we actually have an inverse system, and we take this limit in this, let's call this family H. Of these vector spaces. Okay, so I'll just very quickly, like I said, sort of out of time, I'll very quickly show you the layout of sort of a silly diagram, which may not be very easy to follow without intermediate steps. But I'm going to look at two lines. So here is just some real variable x and real variable y. And I'm going to look at the lines L plus, which is y equal to L plus 1 times x, and L minus, which is y equal to L times x. And here is 1. You can convince yourself that if you try to draw a zigzag curve, which is horizontal, has horizontal and vertical pieces, and the horizontal are at integer levels, so like this, that you can reach any point, starting from here, you can reach any point in this shaded region from any other point that's on these level sets. If you try to go below x equals 1, sorry, this is supposed to be the variable x, that's the line x equals 1. If you try to go below, then that's no longer true because the distance between these two curves is less than 1. And so, in fact, you can set up a suitable, which I don't have time to go into, but you can set up a suitable persistence module and look at capacities which correspond to following zigzags like this. And this is something that will only work for, we get these useful capacities for hat BR1, sorry, for hat BR, when R is greater than 1. And then with those capacities, you can quite quickly just rule out non-squeezing curve for these domains. Okay, so I'll stop there. Thanks.